dear students, welcome to this next video on partial differential equations. So in the third video we discuss surfaces and normals, and in this video we are going to continue with surfaces and normals. So you see what we did till now, that we had this function f of x, y, z, right, and then we saw that this equal to c is a level surface, right? Okay, and then we also saw that gradient of f is normal to this level surface, right? Okay, so now there is another thing which I want to look at, is that can I write this equation in the form of let us just make it capital F so that we can use small f now. So this is, suppose, capital F, doesn't matter actually. So can I write it in this form, that can I separate z in terms of x and y? So that is my question. So I want to know, like, from this relation can I move here, from here can I shift to here somehow. So in doing so we are going to utilize our inverse function theorem, which we defined in the fourth video. So we say that, let us assume let us assume that we are in this x, y, z space, right? And this is actually a surface. So it is a two parametric thing, right? So what we are doing here, that suppose there is a space u and v, and suppose our this x can be written as f1, a function of u and v, y can be written as a function of u and v, z can be written as a function of u and v, right? So now suppose this is there, and suppose we can solve these two for u and v. If we can solve it for u and v in terms of x and y, then we can put that x and y in this third equation, and we get z in terms of x and y. Right now, uh, let us use our inverse function theorem. That says that you can invert it if Jacobian of f1 and f2 with respect to u and v is non-zero. Okay, so if Jacobian is non-zero, that means determinant of Jacobian is non-zero, then we can invert, right? So we will look for those representations where you can invert it. If it can be done, then the surface which was fx comma y comma z equal to c can be written as z is equal to f of x comma y. Okay, so what we said here, the summary is that I had a surface f of x comma y comma z is equal to c. Now because it is a surface, then I know that this is a two parametric thing, right? So what I am doing, I am looking for u and v. Look for u and v such that x is equal to f1 of uv, y is f2 of uv, such that Jacobian of f1 and f2 with respect to u and v is non-zero. Then you can write it as z is equal to f of x comma y, right? So we have fxy minus z equal to 0. So instead of this particular equation here, you will get this equation, right? Does that make sense? And this here, like then we also have this here, you also had z is equal to f3 of uv. So this is called, this here is called the parametric representation of the surface. Okay, because this we already know. So this will be called as a parametric representation of the surface, of the surface. And we know that this parametric representation is not unique. For example, if I have my surface, so note that parametric representation is not unique. Parametric representation is not unique, right? For example, if I have this surface here, x square plus y square plus z square is equal to r square, then you know, everybody knows that we can have spherical polar coordinates. I can have this representation, x is equal to r sine theta cos phi, y is equal to r sine theta sine phi, and z is equal to r cos theta. That is one representation of this surface. And then I can also have another representation of this surface. I'll write that for you. Here you see what are the two parameters, theta and phi are the two parameters. Okay, and we know that this is a sphere and it is defined by two parameters. So what is the other representation? The other representation is x is equal to r 1 minus phi square cos theta upon 1 plus phi square, y is equal to r 1 minus phi square sin theta upon 1 plus phi square, and z is equal to 2r phi upon 1 plus phi square. So this is also another representation. Here also we have two parameters theta and phi. So in a sense we can say that the parametric representation is not unique. But what I want to say here further is, so we are saying that you have your surface, label surface as this, and you are converting it into z is equal to f of x comma y. Now suppose I am interested in this is my surface now, right? Okay, z minus f of x comma y equal to 0, or I can write it as f of x comma y minus z equal to 0. This is my capital F, right? This was the original thing and this is there. Now I know that normal to the surface is, normal to the surface is gradient of f, which is curly f by curly x I cap plus curly f by curly y j cap plus curly f by curly z k cap. This we proved in the first video. So now now my f is f of x comma y minus z. So you can see that c doesn't make any difference because I am going to differentiate. Now if I want to do curly f by curly x, that will be, what will be that? That would be curly f by curly x, right, plus curly f by curly z, curly f by curly x plus curly f by curly z, right? Okay, so what I'm doing here is I'm simply differentiating it with respect to f, differentiate with respect to x. So you'll get curly f by curly x plus curly f by curly z. Just a minute, let me okay, just a minute. So what we are going to do here is, we will keep it like that. So I'll do curly f by curly x. So if I go here, this will be curly f by curly x minus the derivative of this curly f by curly z, right? So this is curly f by curly z, okay, into curly z by curly x, right? So this is equal to, this will be equal to curly f by curly x minus, this becomes p, right? This is how we define. Curly z by curly x is defined as p, curly z by curly y is defined as q, right? So this is there. So we and this is whole, this was equal to c, right? F was equal to c. So if I am differentiating on the right hand side, I'll get a 0. So I'll get a 0, right? So what I get from here, that curly f by curly x is p, right? Similarly, if I differentiate it with respect to y, then what will happen? This will be curly f by curly y is equal to curly f by curly y minus curly f by curly z, which is 1, and then this is 1 actually, right? Then curly z by curly y, and this is equal to c, the derivative will be 0. So you'll get curly f by curly y is equal to q, right? This is this here is small, but you can call it capital also, because in z, z is independent of x, right? Okay. Uh, is z independent of x? No, z is not independent of x, but this is same as the partial derivative, because we are talking about partial derivatives, so this can be capital F also, right? Okay, so this is there, and if I want to differentiate it with respect to z, what will happen? Curly f by curly z, because x and y, we don't have z here explicitly, so derivative would be minus 1. So that means the normal to the surface, so you had this surface x, y, z equal to c, which I wrote as z is equal to f of x comma y, and then normal is this, the normal vector is pi cap plus j cap minus 1 k cap. Okay, so this is the normal vector, and if I am looking for a unit normal vector, so that will be p upon square root of p square plus q square plus 1, comma q upon square root of p square plus q square plus 1, comma minus 1 upon square root of p square plus q square plus 1. So this is a unit normal vector. So this is what we are going to use in future, right? So what you are saying, that if you have a surface, right? You have a surface x, y, z equal to c, right? And then you have to calculate this p and q. What is p? P is curly z by curly x. And what is q? Curly z by curly y. If you can compute this, then the normal is pi cap plus qj cap minus 1k cap. Okay, right? So that is the idea, provided you are able to write it in the form z is equal to f of xy, which comes from the inverse function theorem. So you see, this partial differential equation course is little bit theoretical, right? So there are so many things which you have to visualize and you have to understand, but if you do it well, like you grasp it slowly over the time, it is a very interesting course and very useful also. Thank you for watching this video. Please share this video and subscribe to this channel. Happy learning!